A ripple tank is a convenient way of studying the motion of waves. Imagine, if you will, a thin tank of water, and you're looking at it from above. As you drop something into that tank of water, it would cause a ripple that travels out from the origin of the wave. And I don't know, this is very similar to dropping a rock in a pond or something like that. Now what I'm doing is basically just creating multiple waves one after another. Trying to do that mechanically, or trying to do that manually, is kind of difficult. So what we do is use more of a mechanical oscillator that will continue to make the same wave over and over and over again at a fairly constant rate. Okay, so let's go ahead and start this over again, and let's look at this in a little bit greater detail. What I'm going to do is create this wave and then stop it and look at parts of the wave. The really significant thing to take note of when you look at a freeze-frame view of this wave is the distance between crests, or the distance between troughs. In this case, I'm going to go the distance between one bright line and another bright line, and that essentially is just the wavelength of the wave. It doesn't really matter where I measure that wavelength, whether I measure it out here, or it also doesn't matter like if I measure from dark to dark. Any way you look at it, that still is just the wavelength of that wave. What I would expect is that if I increase the frequency of the wave that was being created, I would expect this wavelength to get shorter. Most of the simulations that we want to look at are best studied by plane waves. Plane waves are similar to point source waves. It's just, instead of a single point origin, it's as though the wave is actually originating from some sort of straight barrier moving up and down. What we want to look at first is how a plane wave like this will reflect off of a surface. So on the left side of the screen, I have a barrier built, and from the right side of the screen, I'm going to basically create some plane waves that come towards that barrier. So what you will see is that when the waves strike that barrier, they will actually reflect back upon the original incident waves, and when that occurs, you get somewhat of a strange pattern that appears. So we have a little pause right before it hits the wall, and then I pause it a couple times as it reflects back, and you can basically see places where the wave is being interfered with. The effects of interference from reflection can really be seen when the wave strikes the barrier at some sort of angle. As before we had the wave coming straight on, but now the wave's hitting the barrier at some sort of angle, and so because it reflects off at an angle, you're going to see the waves interfere with each other in a little bit different sort of manner. One of the things we'll see here when we pause this is that you basically get like a checkerboard pattern that exists out on top of that wave. In a screenshot of this, I've circled the places where you actually have constructive interference. Those two places represent where either a crest is overlapping a crest or a trough is overlapping a trough. You get really maximum water movement at those two places. The destructive interference happens in places in between there that are not necessarily seen very well in the wave tank. Watching waves reflect off of a curved surface is even more interesting. I have here a curved reflector. I would call this a converging reflector because it's going to cause waves to come together. You'll see when those waves bounce off the converging reflector that they have a place where they actually meet somewhere in the center of that curvature, and that place where they meet is actually kind of a special place. In this screenshot of the situation, I've circled that place where the waves come together. That place is called the focal point, and the focal point is pretty important when you talk about curved reflectors like this, because it's the place where you want to bring a bunch of waves together, whether you want to focus sound there or you want to focus light there. Whatever you do, you'll just make that be the place where the waves are the absolute strongest. The other type of curved reflector is one called a diverging reflector. This is one that will make waves spread out after the reflection. So instead of focusing to a place, these actually diverge. This type of reflector makes the kind of curved mirrors where you might look like you're smaller in the mirror than you really are. Refraction is what waves do when they move from one type of material to another type. Usually when that occurs, they will change speeds. In this simulation, I'm showing a plane wave starting in a fast material and moving into a slower material. The slower material on the bottom is indicated by the fact that the waves are closer together at that point. If I have my plane waves come at the surface so that they strike at an angle, you will not only see that the wavelengths get closer together, but you will also see that the wave changes direction as well. This is happening basically because one part of the wave slows down before another part does, and so the direction of its wave motion changes. In this screenshot of this part of the simulation, the white arrow represents the direction that the wave originally was traveling, coming in and hitting the surface at a fairly steep angle, but then as it hits the material and moves into the material, it actually bends down almost more towards the bottom of the frame. This is typically indicative of what we see when waves slow down. The most important application of refraction is how lenses function. Basically, a lens is just a material that will bend light to a singular point and help to create an image. In this particular part of the simulation, you can see where that focal point would be. Different lenses have different focal points. If you send light or any wave into some sort of prism type material, you can see all kinds of neat effects. In this particular simulation, we're not only going to see some reflection, but we're also going to see some refraction happening at all the different sides. I want you to imagine, if you will, that if this was light and if I was shining light into this prism, I could get light to spread out differently depending on what the frequency of that light is. And so we will see that in one of the Waves labs and creating the Pink Floyd on the wall prism that you might be very familiar with. Diffraction is the last thing that I want to show you here with the wave tank. We've seen this already in one of our previous simulations when we were looking at the curved reflector. But instead of looking at the reflection this time, I want you to look at what happens behind that curved surface. You probably are noticing that the waves appear to be spreading out behind the reflective surface. Well, this is an example of what we call diffraction. Diffraction is just the simple idea that waves will bend around barriers when they meet them. Diffraction is probably most notable with sound. The fact that you can hear somebody talking in another room even though you can't see them is an indication that the sound is actually diffracting through the doorway and around the edges of the door as they're making noise. Light also does diffract too, but in order for the light to diffract, it has to either go over a very small microscopic surface or it has to go through a very, very, very small opening.